Hello everyone, welcome to lecture 2 of module 2, which is on SRAMs. In the last lecture, we saw how these memory cells are organized in memory arrays and why we need to take the aspect ratio, or why we need to design memory arrays with aspect ratio of 1. We also saw how these large memories, or how these large memory arrays are kind of divided into several of these blocks, and how that blocks helps not only in reducing the access time, but also helps in the energy saving. At last, we also saw how exactly by intelligently or by cleverly designing these peripheral circuitry, we can actually use memory cells which are having higher density or which use a low number of transistors without degrading on the digital circuit concentrations. In this lecture, we would be looking at the design of SRAM. But before we get into the design of SRAM, let us try to understand the evolution of latches, registers, and let us try to understand first the bistable element which forms the heart of these SRAM cells. So disclaimers remain the same. Let us discuss about circuit elements which show this kind of memory behavior or which can store the system state. So there are two kinds of circuit elements depending upon their variation with time, or depending upon their nature. So one of them is static memory. So in static memory, similar to your combinational circuit design, like you had static CMOS design and you had a dynamic design. So here also, even with memories or registers, we have two kinds of design. One is static design, where we use positive feedback or regenerative properties to realize these registers. However, it is energy efficient only if the content is not updated regularly. If the content is updated regularly, then you have a lot of power dissipation, right? So static memories are energy efficient as long as the contents are not updated regularly. For instance, this boot time configuration data. Whenever you turn on your computer, it loads this boot time data, right? And this boot time data doesn't change much unless you are changing it by going into the boot settings. So this is kind of data where static memories would be efficient when they are being used. Now, how can you realize this static memory? Using positive feedback. So what are the positive feedback elements which are available in circuits? So we have multi-vibrator circuit, and in multi-vibrator circuit also we have different flavors. Most common of them is a bistable element. So what exactly is a bistable element? As the name suggests, it consists of two stable states, which can be classified as logic level 0 or logic level 1, or which can be used to store a logic level 0 or logic level 1. It can have several metastable states, but it has got only two stable states. And apart from this, we also have monostable and astable circuits, which are used for different purpose. For instance, like ring oscillator or something. I'll be discussing about these two elements as well towards the end of this module. Now, once we have discussed about the static memory, let us look at the dynamic memory. Similar to the combinational circuit discussion, even here the dynamic memory stores data for a short time as charges on a parasitic capacitor. Now, since the data leaks soon, I mean, because of the we already discussed that there are several charge leakage mechanisms, right? So typically the storage time on those parasitic nodes or high impedance nodes is some millisecond, and since it's some millisecond, we have to update them regularly. And dynamic memory is particularly best when we are using when they are being used for systems in which they are clocked continuous. Now, we know that there are several problems like charge leakage because of those leakage current through subthreshold current or diode leakages, as well as there is this charge sharing problem. Whenever we are working with this high impedance node or internal node capacitances, there would be these problems, and there would be crosstalk as well as other problems. But how we can handle this problem? Now, since the data is stored as charge on that high impedance node or that internal capacitor or any capacitor in general. So when you have these problems of charge leakage and charge sharing, then in order to maintain the state of the data, in order to read the correct data, maintain the state of the correct data, you have to do what? You have to refresh it periodically. Why? Because you need to compensate. I mean, you need to make the data, you need to retain the data in its correct form. So you have to periodically refresh it, and you have to compensate in order to compensate for the charge leakage and charge sharing problem, right? And as we discussed, even for combinational circuit design, even when you use dynamic design for realizing these registers, it's a simpler and faster approach, and also the power dissipation is less. At the same time, it is useful for storing clock data. I mean, the thing is, if it is not being updated regularly, or if it is not being clocked regularly or refreshed regularly, then you will lose the data, right? So there's this problem. See, refresh actually adds to a lot of power dissipation here. But if you just consider the power dissipation of the individual dynamic cell or dynamic register, that is low. So here I would like to point that out. So refreshing it consumes a lot of energy. However, if you talk only about the dynamic register, its power dissipation is less. I mean, standalone, its power dissipation is less. But if you talk about this refresh process, then that takes a lot of energy. And that will be, evident when we discuss about, even, the memories like dynamic RAM and static RAM, so on. I mean, SRAM, DRAMs, and so on. When we discuss that after this module, that will become very clear. So at this time, you just remember that dynamic RAMs, or dynamic memory is actually better as compared to static memory when we have, when we are storing a clock data that is changing at every cycle. And if the data is not changing much, for example, if it's a boot time configuration data, it's not changing much, then static memory is something which is more efficient. And these are the two ways of designing your registers. Now, even I was pretty much, when I was speaking in the last lecture, sometimes I use latch, sometimes I use register, but there is a difference between the two. And in this lecture, I would clarify the difference. See, sequential circuits, whenever it is being clocked, and whenever you're talking about switching or, sampling at the clock edge, it's a register, right? Latch is a different thing. So let us discuss what exactly is latch. So latch is nothing but a level sensitive circuit. So in latch, we told that the data is sampled in a register only at the clock edge. However, that is not true for a latch. In a latch, it's a level sensitive circuit. So let us see what are the different types of latch. There's a positive latch and a negative latch. So as long as, if it's a positive latch, as long as the clock is high, that is, the clock is at logic level 1, whatever data is there at D, which is its input, it will be transferred to Q, or the latch is transparent whenever the clock is at logic level high, right? So latch is something which is transparent at only a particular logic level of clock. If it is transparent for positive or logic 1 of clock, it is called a positive latch. If it is transparent for negative, or I would say like logic level 0 of the clock, it's called a negative latch. So this is how you define a latch. As long as the data is as long as the clock is high for positive latch, D is transferred to Q. As long as the data is present, or as long as the clock is logic level 0 for negative latch, D is transferred to Q. This latch is transparent. So for positive latch or transparent high, this is another name for positive latch, transparent high. D is passed to Q as long as clock is high. Now what happens when the clock gets too low here? When the clock gets too low, whatever data was there immediately before this, it's stored, it's held, it doesn't change. So whatever was the value of this D immediately before this edge, when the clock was high, that is retained when the data is, or when the clock is logic level 0. So logic level 1 for positive latch, D is transferred to Q. Logic level 0, the data is held. What data is held? The data which was sampled immediately before this clock edge. Similarly, for negative latch, everything is complementary. It's a dual of it, right? Now let us talk about registers. What are registers? So registers are basically edge triggered. The sample input only at clock transitions. So here I told that as long as clock is high or clock is low, depending upon whether it's a positive latch or negative latch, D is continuously sampled to Q. But in registers, that's not the case. D is sampled to Q only at clock transitions. So if it is 0 to 1 transition, I mean, if it's low to high transition, if the data is being sampled at low to high transition of a register, it's called a positive edge triggered register. And if it is being sampled at high to low transition or 1 to 0 transition of the clock, then it's called a negative edge triggered register. Now, how are these registers constructed? So typically, they're constructed using these latches itself. And they use this master-slave configuration. So whenever you discuss about sequential circuit, you hear this term a lot, master-slave architecture. And even for your placements, they'll definitely ask you master-slave latch-based flip-flops. I mean, not definitely, but it's a very common question in nearly all the interviews. They'll first ask you master-slave configuration, then they'll ask you, set up hold time, and then they'll try to make complex network of them, and then ask you to calculate set up hold time, or whether the or the maximum clock period or something like that. So be prepared regarding that, right? So what exactly is master slave architecture? So it's the most common architecture to construct registers with latches. So what we do is we cascade two complementary latches. If we cascade a positive latch followed by a negative latch, it's a negative edge triggered register. If we cascade a negative master with a positive, like if we cascade a negative latch as master and positive latch as slave, then it's a positive edge triggered register. If we cascade a positive latch as master followed by negative latch as slave, then it's a negative edge triggered register. Now, there's a huge discrepancy in the definition of this register and latches in the literature or in even books. There are different definitions given in the books, in the literature, and so on. But in this course, we would be following the convention which is stated in the Rabai's book, and that simply says that register is any element, any storage element which is edge triggered. How exactly is latch defined? So latch is any level sensitive device. And what is a flip-flop? So I was using register and flip-flop invariably, right? That is true in some sense, but you should know that the way Rabai defines it is flip-flop is any bistable element, right? But what we are looking ahead or what we will be working with is a register. So whatever we are saying that flip-flop is actually in the sense of register. Any bistable element we can call a flip-flop, but in the last lecture I used register and flip-flops invariably. That is fine to some extent. But from now onwards, we will refer registers as any edge triggered storage element and flip-flop as any bistable element, right? So now we have been talking about this bistable element for a long time. That it's a basic component. It's the most common way of implementing static memories. Let us look at a very simple form of a bistable element. So I told that static memories use this positive feedback to realize bistable elements. But what exactly is bistable? That also we discussed that it's any circuit having two stable states that may represent logic level 0 and logic level 1. Let us see a very simple form of bistable element, which is obtained by connecting two inverters and then taking a feedback from output of this to the input of the first. So here you can see that we have V in 1. I mean the input is at V in 1. It goes to V out 1. Now V out 1 is actually input of the inverter 2. So V in 2 is nothing but V out 1. And because of this feedback, this V out 2 becomes input of inverter 1, right? So V in 1 is V out 2. Now let us look at the VTC of these CMOS inverters. So you remember from our discussion in static CMOS module that this is somewhat this is how the VTC of a CMOS inverter looks like. So this is V in 1 versus V out 1, that is VTC of inverter 1. This is VTC of inverter 2, that is V in 2 as a function of V out 2. But now we see that this input, this input of 2 is actually output of 1, and this output of 2 is actually input of 1. So there is a possibility that we can represent it on the same axis, similar to the load line analysis, right? So there is a possibility that we can represent them on the same axis. Let us choose that same axis as V out 1, which is equals to V in 2. Sorry, yeah, V out 1, which is equals to V in 2, and V in 1, which is equals to V out 2. So if we want to represent this on this axis, similar to finding the load line. Why do we find load line? So as to find out the possible possible operating points, right? So if V in 2 is given input, so V in 1 is what? V in 1 is nothing but V out 2. So we want to express this V out 2 here. We want to bring this axis here. So if you do that, it's simply obtained as flipping of this along this direction. So if you just flip the axis here of this curve, because you want V out 2 on the x-axis, right? V in 1 is equals to V out 2, and you want that on the x-axis in order to find the possible operating points. So how can we do that? So let us plot V in 2, which is nothing but V out 1 on the y-axis, and correspondingly, let us draw V out 2 on x-axis. So when V in 2 is large, what is the value of V out 2? It's 0. When V in 2 is small, or when V in 2 is 0, what is the value of V out 2? It's 1, right? So this is nothing but axis. This is simply rotation of this. and we have simply transformed the axis, like we have simply made or plotted V in 2 on the y-axis and V out 2 on the x-axis. Why have we done that? Because V in 2 is V out 1, V out 2 is V in 1, and we want to make the axis same so as to do the load line analysis and find out the possible operating points of this circle, right? So once we have done that, what do? We just superimpose them, right? So once we superimpose them, what do we find out? That this is the characteristics of inverter 1, this is the characteristics of inverter 2. So we look for the intersection points, right? So we find out that there are these 3 intersection points, A, B, and C. Now, if gain of inverter is larger than 1, that is, if the gain in the transition region is larger than 1, then A and B are the only stable points, and C is a metastable points. Why do I say so, right? I say so because, let's say if there is a noise in the system, let's say we have biased the system at this quiescent point C or metastable point C, and let's say if there is a noise in the system, let's say the noise actually deviates this C, like noise is present in the system and it deviates it towards left, given by this blue arrow, right? So if it deviates it towards left, now what is our input then? So C is typically at VDD by 2, right? Now if it's deviated towards less than VDD by 2, what is our V in 1? It is less than VDD by 2. So if V in 1 is less than VDD by 2, if V in 1 is less than VDD by 2, we get the output V out 1 here, right? V in less than VDD by 2, we get V out 1 here. Now this V out 1 is what? This V out 1 is actually V in 2. That is, this point actually, this voltage actually is input to the second inverter. So if this voltage is input to this inverter, the output will lie on this line, right? So corresponding to this voltage as input, corresponding to this V in 2 as the input to the second inverter, the output that you get here, output that you get here is this, right? At this voltage, see, I don't know if it is making sense to you guys or not, but let's talk about this C point. Noise deviated it, like it was, we biased the system at VDD by 2. Always there would be some noise. It deviated it towards the left. Noise amplitude is negative and the RMS value is negative. It deviated it towards the left. Now, since it's deviated towards the left, now what is our V in 1? V in 1 is less than VDD by 2. V in 1 less than VDD by 2, what is V out 1? We follow this curve. We get that V out 1 is this. Now, this V out 1 is what? It's the input of this inverter. So, this voltage is actually this voltage here. This voltage here. This is the voltage, this is V out 1, right? This is the input to this inverter. And what is the characteristics of this inverter? It's this, in this transformed axis. So, corresponding to this as the input, what is the value that we are getting? Or let me tell you like this, corresponding to this input, corresponding to this V in 2 as the input, intersection with this curve is on, like intersection with this curve is at this point. So, corresponding to this value of V in 2, we are getting V out 2 as this point. And now corresponding to this point as V out 2, like this point is now the input of the first inverter. So corresponding to this point as V out 2 or V in 1, what is the corresponding V out 1 that we are getting? It's this one. We'll look at the intersection with this line. Okay. So a small deviation here is actually amplified and regenerated. So small deviation in the noise gets amplified and regenerated, and we reach either point A or point B depending upon the noise direction. Similarly, if the noise was positive, so our system stable, like our quiescent point would be, now VDD by 2. If it is shifted by noise from VDD by 2, it would be greater than VDD by 2. So if V in 1 is now more than VDD by 2, what is the value that we get? If V in 1 is more than VDD by 2, if V in 1 is more than VDD by 2, if it is shifted here, then corresponding to this voltage, what is the V out 1? This is the V out 1, right? This is the value of V out 1 because we'll look at the intersection of this, intersection on this axis. For this value of input, because of noise, what is the value of V out 1? It's this. Now, what is this V out 1? This is input of 2, right? This is this value. This is input of 2. Now, if this is the input of 2, what is the output? We'll look at the intersection at this. So from here to here, we'll draw a line and it intersects at this point, at this point. So this now becomes what? This becomes V out 2. And this voltage is what? This is input of the first inverter. So How will we get the output of the first inverter? If this input is applied to the first inverter, what is the output? We look at the intersection with this axis and it is here. So we get to point B. So any noise or any deviation from point C, which is definitely going to happen because noise is inevitable in a system, it will get amplified and regenerated around the loop, and then system will go from C to either point A or point B. So these are the stable states, bistable states, because loop gain, or I would say the gain at these points, at points A and B, is smaller than 1. Whereas the loop gain at point C is quite larger than 1, right? That is true. So this is a bistable element, a very simple bistable element. Now, how can we change the state of this bistable element of flip-flop? How can we make it toggle? There are basically two ways. One is to overpower this circuit by making loop gain larger than 1 at A or B. So A or B are stable points, right? Where the loop gain is less than 1. In order to transition, or in order for transition to happen, you must make the loop gain larger than 1 at either point A or B at the stable states. So how can we do that? If we apply a trigger pulse, then we can make that. Now, how exactly we apply a trigger pulse? So let's say this is our bistable element. We have a large transistor. Why we make this MOSFET larger? Because, if this MOSFET is not larger, then we cannot overpower this. If the driving strength of this is not larger, we cannot overpower this. So this is also kind of ratioed logic, right? However, let me not go into the details. I'll go into the details when I'll be discussing about SRAM, static RAMs, in the next module, which is heavily used in the cache memory. You know that cache memory is the most expensive memory. Larger the amount of cache memory, more expensive your system is. So cache memory is very important. And this is the system which is used in cache memories. So it's very important, right? Understanding this is very important for you guys. Also, it's also very important from placement perspective. So it will be better for you guys to read it well. Now, what I say here is that width has to be larger than the total delay around the loop. So what I'm saying that, let's say the system was stable at, let's say, point A. So what is point A? Point A means what? Point A means V in 1 is 0. V in 1 is 0. V out 1 is what? V out 1 is 1. V in 1 0. V out 1 1. V in 2 is 1. And V out 2 is 0. Right? Let's say we are at point A where V in 1 is 0. Let's say we are at point A, V in 1 is 0. Now we want to transform it to point B. What is at point B? So at point B, your V in 1 is equals to 1, V out 1 is equals to 0, V in 2 is equals to 0, and V out 2 is equals to 1. Right? So we want to flip from point A where V in 1 is 0 to point B where V in 1 is 1. So what we do, if it is at point A, that is, if this V in 1 is 0, we apply input as VDD. And we apply enable signal as VDD plus VT so that whole VDD is passed, because otherwise it will pass VDD minus VT, right? So let's apply that, and then let's try to flip this volt. Let us try to overpower this volt. Now, why I say that width has to be larger than total delay around the loop? Because let's say if I apply this signal for only one propagation delay. So if I apply this signal for only one propagation delay, this is 1 for 1 TP. That is, this node will get 1. So this node will get what? After 1 TP, this is transferred here, right? So this node is 1, this node will be 0. However, this node earlier was at logic level 0. So if this signal is now removed, this node will try to force this node again back to logic level 0. Right? So this feedback actually forces it again to logic level 0. If this input signal is applied only for TP or only for duration which is less than 2T. This signal actually doesn't propagate and come back here. It doesn't reinforce the feedback. So there is a competition between feedback and this input signal if the applied signal width is less than the total delay around the loop. Now let's see what happens if we apply this signal for more than 2 TP. So if we apply 1 here for more than 2 TP, this 1 is transferred to 0 at the end of 1 TP, and this 0 is transferred to 1 at the end of 2 TP. And then this feedback is also sending 1 here. So even if you remove the input now, feedback is 1, and this node is also earlier at 1 because of the previous input applied. So this feedback is reinforcing it. There's no competition between the feedback and the applied input, right? So this input has to be applied for a width or for a duration which is more than the total delay around the loop, so that feedback also reinforces it and it doesn't compete with it. right? So this is one way of changing the state of flip-flop. There's another way as well, and that is most common. I mean, in embedded system, embedded memories, that is very common. What is it? We cut the feedback loop. So we just remove a feedback loop, write the correct data, and then reconnect. How can we do that? Simple way to do that is to introduce a pass transistor in the feedback, right? If there's a pass transistor in between, just by the control signal, we can cut the cut the feedback loop. Then we can insert another signal and write the data, and then we can reconnect it by just applying the control signal on the pass transistor. So this is most commonly used in multiplexer-based latch, and that is most common in your embedded memory. What exactly is embedded memory? So the memory which is closest to the processor, that is called embedded memory. Somewhat far is cache, and then farther from that is your main memory. So registers that are present in your processor, that are these mux-based latches. Then cache memory that is present, that is static RAM. Then what is the main memory? Main memory is your dynamic RAM or DRAM. And then what is HDD or your solid state drive? That is your flash memory. So these are different hierarchies of memory in your computer system, right? And we'll be looking at all of them in the next module. So don't worry. Now with this understanding of the bistable element of the flip-flop, let us look at what exactly is the SRAM cell. So here, what I'll be talking about is a 6-transistor SRAM cell, which is the industry standard SRAM cell. You can have SRAM cells having less than 6 transistors or even more than 6 transistors, depending upon what specifications or what applications you need. So this is the industry standard, and that is why I have chosen this as a typical example to study the operation of SRAM cell and their performance. So the circuit here represents a 6-transistor SRAM cell. So you have a bit line bar. So you see that instead of having one column to represent the data, you have 2 columns to represent the data. 2 complementary columns. One is bit line bar, and you have a word line, similar to that memory organization thing, right? So here, what do we have is we have these 6 transistors, where this M1, M2 is one inverter, M3, M4 is the other inverter. So this combination of M1, M2 and M3, M4 forms inverter pair. I mean, let us indicate inverter 1 by combination of M1, M2, and let us indicate inverter 2 as M3, M4. And what are these M5 and M6? These M5 and M6 are called the access transistors, which are nothing but they are used to program this. They are used to change the state of this cross-coupled inverter pair over here. So this you can think like an access transistor, M5 or M6. So here, this is only one access transistor. If you include another access transistor here, let's say this is M5, this is M6, then you make a SRAM cell. How? Let us look at that. So I told that these are 2 inverter pairs which are cross-coupled, and M5 and M6 are called access transistors, which are basically used to read the data present at these nodes, or change the voltages or change the data present at these nodes. That is why the name access transistor. So if you redraw this, it will look something like this. So this is inverter 5. Sorry, this is your access transistor M5, and the output of inverter 1 is connected to it here like this. And the input is coming from M6. Input is coming from M6 here, right? Similarly, if you look at this M6, the output of inverter 2 is connected to M6 here, and the input of inverter 2 is actually coming from M5 like this. So this is another way of representing a SRAM cell, where we have a cross-coupled inverter pair. This node is Q, this node is Q bar. M5, M6 are the access transistors, which are turned on and off with the help of these word lines. And the data is kind of read on or written through these bit lines. And here, instead of only a single bit line, we have 2 complementary bit lines, BL and BL bar. So there is this, famous phenomena in SRAM cells, which is called read-write conflict, which we'll discuss in detail in the next section or next lecture, which is very important. And here, I have been telling that in the memory organization, I told that we can work with even 1 bit line. However, in the case of SRAM cell, I'm saying that we have a bit line and a bit line bar. We have 2 bit lines, both are complementary. So the question that immediately may arise in your mind is, can we work with only single bit line? in SRAM? Why do we need both bitline and bitline bar, right? So that is one question which, if you think judiciously, it will definitely arise in your mind. So to, make you think, what I have thought is, in your examination, I would give you a frame your own question material. I mean, I would ask a question which will say, frame your own question and justify, give your answer also, and justify why the question should be graded for the particular marks that have been given, that have been allotted to it. And the important part about this is, this question should not be a part of the lectures. It should not come from the reference books. This question should be something which came into your mind while you were going through this course, while you were reading these lectures, and then you identified, or then you found out their answers, and you think that you are an instructor, and through the most difficult question that you came across this course, in that frame your own question. So one question I'm already leaking out to you, and that would be a frame your own question. And this is one of the important materials. So I would say this can be one of the good questions for that frame your own question. Right? Now with this introduction to SRAM cell, 60 SRAM cell, where we have two cross-coupled inverter pairs whose content can be addressed or changed with the help of these access transistors, let us look at the read operation and the write operation in SRAM cell. So typically in any memory element, there are three operations which are very important. One is read, second is write, and third is hold. Here in this lecture, we will be covering the read operation and the write operation in SRAM cell. So this is the typical 60 SRAM cell. So what happens in the read operation? What we do is, although these bitline and bitline bars are complementary by definition, I mean, this is bitline and this is bitline bar, that is, whatever logic is present on bitline, the complement of that should be present at bitline bar, according to its definition. Although that is the definition, during the read process, what we do is, we pre-charge both bitline and bitline bar to VDD. Now, how can we pre-charge a line? So this BL or BL bar consists of several capacitance components. What are those capacitance components that are available on BL and BL bar? First one is the CGD of this M6, right? Let us consider only BL first. So the first capacitive component connected to this BL is the CGD of M6, right? CGD of M6. And this is one SRAM cell. There are several such SRAM cells connected between BL and BL bar. So you will have several such CGDs. So if we include a capacitance over here and we name it CBL, then CBL will consist of all those CGDs. So let's say if there are N cells, it would be N times CGD. On top of it, you also have this interconnect wire capacitance, right? Since this is a line, this line will have an interconnect capacitance, and that interconnect capacitance will also be added to this CBL. What apart from that? So apart from that, we saw that for all these bit lines, there was a sense amplifier which was connected to these bit lines, and that we told was helping in generating rail-to-rail swing and improving the speed, read speed. So that sense amplifier would also be connected at the end of this array. So the input impedance of that sense amplifier will also be, a part of this CBL. What else? So on top, you will have a pre-charge circuitry as well, which kind of pre-charges this bitline and bitline bar initially for a read process. So even the capacitance of that pre-charge circuit, that would be a component of the CBL. So this bitline will actually have a capacitance CBL, which is typically in picofarad range. And what would be the components? The components would be first the CGD of all these SRAM cells, CGD of all these access transistors connected to this BL. Its interconnect capacitance, that is parasitic. Input capacitance of that sense amplifier, as well as the capacitance offered by this pre-charge circuit at the top and sense amplifier at the bottom. So those are capacitances form CBL, and similarly you'll have CBL bar because all of them are connected between bitline and bitline bar. So whatever is CBL bar will also be the same. Then what we do initially in the read processes, in the read operation, what we do initially is, with the help of this pre-charge circuitry, which is on the top, we pre-charge BL and BL bar. The capacitances present at BL and BL bar, we pre-charge them to VDD. Regardless of them being complement of each other, we precharge them to VDD. Now what we do is we assert word line high. Now what happens when we assert word line high? When we assert this word line high, we kind of turn on M5 and M6. Now the thing is, if we apply VDD on this word line, then because these access transistors are NMOS, there would be a VT drop across them, right? Because NMOS doesn't pass logic 1 perfectly. So to mitigate that issue, what people typically do is they bootstrap these word lines. What is meant by bootstrapping? They apply VDD plus VTH on word lines to avoid this VTH loss, right? I mean, even if there's a VTH loss, if you apply VDD plus VTH, effective voltage that will be passed will be VDD, right? This bootstrapping has another meaning in terms of layout. So that also we'll discuss when we talk about DRAMs and all. But here you just understand that, we apply VDD plus VTH to avoid this VT loss through these NMOS transistors, which do not pass a perfect one. Now, what this read operation means is, read operation simply means that whatever value of Q and Q bar are here, that should be reflected on bitline and bitline bar. And the content of this Q and Q bar, that should not be changed. That is, the read should be non-destructive. Data on Q and Q bar should not be changed. Only whatever content was available on Q and Q bar, that should be reflected now on bitline and bitline bar. Let us say that, Q is equals to 1 and Q bar is equals to 0. So in that case, if it is ideal reading, like if it's ideal read process, then BL should be equals to 1 and BL bar should be equals to 0, because Q bar equals to 0 and Q is equals to 1. And that will represent that a logic 1 was read, or a logic 1 was stored here and that was read subsequently. Now, in this condition, I mean, when Q is equals to 1 and Q bar is equals to 0, the kind of circuit when we have BL and BL bar both at VDD, precharge to VDD, and WL asserted high, the kind of circuit that we end up having looks something like this. So we have these capacitances, CBL and CBL bar, which are charged to VDD. Q is equals to 1, Q bar is equals to 0. Since Q bar is equals to 0, this M3 is kind of cut off, so we haven't shown it. And also, since this Q bar is equals to 0, this M4, its gate is grounded. So this is what happens in the, this is what happens when, you apply all these pulses in the order that I've told you. Now, if you look at this carefully, what exactly is happening here? So if you look at this portion, you have this node, which is basically your VQ bar. Let's say that this is your Q bar node, or where your Q bar is stored. And let us call this node voltage as VQ bar. So what exactly is happening here? This CBL bar is trying to charge this node, or it's trying to pull this node towards VDD through M5. And this M1 is trying to discharge this to ground. So basically what is happening? This voltage VQ bar is kind of being pushed towards VDD through this M5 and CBL bar. And at the same time, it is being pulled towards the ground via this M1. Now, the exact value of voltage at VQ bar depends upon the relative pulling strengths or relative driving strengths of M5 and M1. However, the thing that we already told is that in the read process, the content should not change. That is, this Q bar, if it is 0, it should remain 0 and it should not go to 1. Or this Q, if it is 1, it should remain at 1, it should not go to 0. Now, if you look at this diagram, here, you notice that, this BL bar is trying to increase the voltage over here, while this M1 is trying to reduce the voltage of this node. Now, if the voltage at this node, that is, if VQ bar is greater than the VM of this transistor, or if this VQ bar, voltage at VQ bar, because of this, CBL bar pushing it towards VDD, if somehow this voltage over here, if this voltage at VQ bar increases beyond the switching threshold of this inverter 2, then what happens? If this VQ bar voltage increases beyond VM of inverter 2, the output becomes 0. Earlier, Q equals to 1 was stored, but if somehow VQ bar increases above the threshold, switching threshold of this inverter 2, then it will flip the content of its output, and this Q, which was originally at 1, will go to 0. So what we have to ensure for non-destructive read or for non-disturb read, what we have to ensure? We have to ensure that this voltage at VQ bar should not rise beyond the switching threshold of inverter 2, right? How can that be ensured? That can be ensured by properly sizing M5 and M1. We'll see that later, but the point that I'm trying to make here is, if somehow this M5 pushes this VQ bar above the switching threshold of the second inverter, inverter 2, then we will end up flipping the content of the cell. We would end up making Q is equals to 0. And in that case, what we'll end up having is a destructive read. Now, what essentially do we want? What exactly is this VQ bar? If you look at this circuit, this VQ bar is nothing but the drop across this M1 transistor, right? So what we want inherently is that this drop should not be large. If we do not want a large drop across this transistor, what we can do is we can design it with a low on resistance or a high W by L ratio, right? Now, as I discussed earlier also, this M5 is trying to pull this node up while this M1 is trying to pull this down. So the driving strength of M1 and M5, the competition between the two decides the value of voltage at VQ bar. And if we want this node to be, if we want this node voltage to be smaller, much smaller than the switching threshold of this inverter, then what we should ensure is, we should ensure that the driving strength of M1 is higher than the driving strength of M5. Now this ratio of the driving strength of M1 to that of the driving strength of M5, which is typically called the cell ratio, given by W by L of 1 divided by W by L of 5, we want this to be as large as possible, so that this node is not pulled towards, the VDD much. Now let us talk about a scenario. I mean, this cell ratio is a very important phenomenon. It's a very important kind of component while designing any SRAM cell. For non-destructive read, you have to ensure that this constraint on cell ratio is always satisfied. That is, cell ratio should be greater than 1. Also, now let us look at a particular scenario. Since this SRAM cell is made up of 6 transistors, for improving the density or for having a large density, we would want that ideally all these transistors should be minimum sized, right? So let us say that M1 is minimum sized. Now, if M1 is minimum sized, that is, if its W and L are W min and L min, then how can we have a cell ratio which is larger than 1? Let's say that the width of M5 is also minimum. In that case, the only way to reduce the driving strength of M5 as compared to driving strength of M1 is to increase the length of M5. Now, is that a feasible solution? Let us look at what are the implications of that. If we increase the length of M5 to reduce its driving capability as compared to M1, then typically what we are increasing? We are increasing the capacitance CGT value. Why? Because CGT depends on area of the transistor, right? So if we increase the length, the capacitance increases, and hence we increase CBL bar. Why we increase CBL bar? Because there are several of these, CGTs connected on this bitline bar. And we are increasing all these CGTs by having a larger length of 5 as compared to 1. So in that case, we are increasing CBL bar. And once this capacitance is increased, the time it takes to charge or discharge this capacitor, that would increase, right? So as such, you will have a slow read. So the only option that we are left with is to increase the W of M1, and that is a feasible solution. Now, let me give you some food for thought. What if we do not precharge these CBL and CBL bar to VDD, and instead we precharge them only to VDD by 2? What are the advantages that we are going to get in that case? This is a typical case that we discussed when we are talking about, the role of peripheral circuits. That the swing on the BL and BL bar, if instead of having a rail to rail swing, that is VDD and VDD to 0, if we have it as VDD by 2 to 0, if we reduce this swing, what are the implications? Can we even perform write or read? Let us, you give a thought to it and let us discuss it in our discussion session. So with this, the read operation is you now know enough about the read operation in SRAM. Now let us go ahead and look at the write operation in SRAM. So write typically means we have to flip this content which is already written into the cell. So if Q is equals to 1, Q bar is equals to 0, we have to flip it to Q equals to 0 and Q bar is equals to 1. For this, what we do? First, we apply appropriate voltages on bit line and bit line bar. Here, let us take the case that Q is equals to 1, Q bar is equals to 0. So now if we have to flip this Q equals to 0, we'll apply 0 on BL and we'll apply VDD on BL bar to flip this Q bar to 0 from 0 to VDD. And then what we do? We again assert the word line high so that M5 and M6 are turned on and we can access these internal nodes. Now the circuitry looks something like this, right? So what we are doing now is we are applying BL bar equals to 1 to flip the content of Q bar equals to Q bar from 0 to 1, and we are applying 0 here on the BL to flip the content of Q from 1 to 0. However, we saw that we have already sized M1 and M5 such that even if we apply VDD here, VQ bar cannot change, or VQ bar cannot increase beyond the threshold voltage, switching threshold voltage of inverter 2. So what I'm trying to say is, because of the appropriate cell ratio, or because we have already sized M1 and M5 such that we perform non-destructive read or non-disturbing read, by doing that, what we have ensured is, even if we apply VDD on BL bar, the voltage at this VQ bar does not increase above the switching threshold of inverter 2. That is, we cannot flip the content of this cross-coupled inverter pair by applying VDD on this bitline bar. Why? Because we have already sized M5 and M1 in such a way. We have already satisfied the cell ratio criterion. So in that case, how can we flip the content of this cross-coupled inverter pair over here? We can do that from the right-hand side. We can do that with the help of M6. How we can do that? Let us see that. So what happens here, if we focus on this side of the circuit, this M6 is trying to pull this node, this VQ, towards ground, which we want, while this PMOS FET M4 is trying to pull it towards VDD, right? So the voltage at VQ is kind of dictated, or it's kind of being pulled towards the VDD by this M4, and it's being pulled towards the ground by this M6. Now what we have to do? What we have to do with this VQ? We have to make this VQ smaller than the threshold, switching threshold of inverter 1, so that the output goes from 0 to 1. If input voltage is less than the switching threshold, output goes to 1, right? That is what happens in a typical inverter, VM. Vin less than VM, output goes to 1. So this VQ is kind of given as the input to the first inverter, and if we ensure that the voltage at Q, the voltage VQ here, is reduced below the switching threshold of inverter 1, we'll be sure that this Q bar goes from 0 to 1. And that is what we have to ensure. So we have to design M4 and M6. I mean, we have to design M4 and M6 to have a situation where the voltage at this node Q reduces below the switching threshold of inverter 1. So what we have here M4, which is trying to pull this towards VDD, M6, which is trying to pull this down. So here, what should we have? Since we want to pull this towards the ground, or since we want this to be small as compared to the switching threshold of the first inverter, what we have to ensure is, we have to ensure that the driving strength of M6 is higher as compared to driving strength of M4, so that this voltage is smaller, and as such, the content of this, like output of this inverter, is flipped. That is what we have to ensure. This ratio of the driving strength of M4 as compared to M6, or W by L of 4 divided by W by L of 6, is actually called pull ratio. So these are the two ratios, cell ratio and pull ratio, which kind of enable appropriate design of SRAM cell, so that we have non-destructive read and we ensure effective write operation as well. Now let us look at a particular case. Let's say that both M4 and M6 are minimum sized. So if M4 and M6 are minimum sized, is the driving strength of M6 higher than the driving strength of M4? Yes. And I say that pull ratio is satisfied. Constraint on pull ratio is satisfied. Why do I say so? because M4 is a PMOS and M6 is an NMOS. And we know that mobility of holes is lower than that of electrons. Because of the reduction in the mobility of PMOS, like in PMOS, the driving strength or its kind of on resistance is higher as compared to the on resistance of M6. So the driving strength of M4 is lower as compared to the driving strength of M6, even when they are minimum sized, just because your M4 is a PMOS and M6 is an NMOS. And in typical design of SRAM cells, the cell ratio is something which needs more attention, and this pull ratio is something which is easier to satisfy even with minimum sizing of these, like even when the transistors M4 and M6 are minimum sized.